Alright, so this is the sixth question of the Grind 75. This one is called Invert Binary Trees. We're given 15 minutes, so let's start the countdown. So given the root of a binary tree, invert the tree and return its root. Okay, let's see what invert means. Root is here, 2, 7, 1, 3, 6, 9. Output. Okay, so it seems like we just flip it across the vertical axis. So I will draw out, but let's see. Okay, let's actually look at the implementation. So they gave us an implementation of a binary tree. So let's take a look at it. All right. So a node contains a value, a pointer to a left node, and a pointer to a right node. We can instantiate a tree node as null, as one with just a value, or as one with a left, right, and a value. Okay. So the root of a binary tree. Okay, it doesn't necessarily have to be um, complete though, and it's not like fully fleshed out like it is like this, but let's see. We should still be able to switch. So, I mean, if we just think about this really quick, just looking at the example they gave to us. So we start here. I think we can just, so maybe set left child equal to a temp, then set left child equal to what right is, and then set right child equal to the temp. So that will switch these two nodes, and then everything below it will also get pushed over. And then I think all we need to do is recurse on the left and right. So we are not returning anything, we are just simply modifying the structure. And I don't think there's really anything else to it. We can think of the runtime, it should be log n, because we were just going from the top of the tree to the bottom of the tree, and it's a binary tree. So let's see. I'm just trying to think. So let's look at some of the edge cases maybe. Um, yeah, I mean, this is like it in its most basic form. Um, can a binary tree be 0 or 1 in length? Possibly. I think it can, because it can be a single node with just two nulls. So maybe we'll say, let's write down the steps we're going to take actually. So check if input is 0 or 1, just the standard kind of check. And 1 second. We're also going to check if we're just going to do the typical switch thing, which is here. I'll say temp equals left, left equals right, right equals temp. Okay. And I think there's one more thing, and what was that? Is simply recurse left, recurse right. I really don't think there's much else to this. This is a pretty straightforward problem. We just need to terminate. So yeah, if input is 0 or 1, then we just return. It should be void, or no, tree node. So invert and return its root. Okay. We do want to return the root. Okay. I probably should have paid closer attention to that. So, I mean, I could make a function inside of that because, I think I honestly might just do that because we don't, I'm not really seeing how we can stay on the root the whole time. And let me go back to the graphic. Stay on the root the whole time, but then recurse down to its children. I mean, the procedure we're doing, it's recursive, so basically what I'm going to do is just like take hold of the root, pass it into some function, and that function will do all of the logic. So yeah, okay, all right. So that should be totally fine. So let's do that. So I'll make public, this will be a void function, and I will call it tree inverter, or maybe invert tree logic. This will take a tree node, which will be the root, and let me actually switch over to the screen so we can see what we're doing. So I'm going to make the second function. Basically, all I'm going to do in our main function is pass in, let's see, yeah, I'm going to pass in root into invert tree logic, and then I'm just going to return root. Our root should never change. The pointer to the root will always be the same in this function, specifically. So I'm just going to worry about what happens in this other function here. Okay. So we're going to check if root is equal to null, or I guess left is equal to null and right is equal to null. There's no isLeaf method in this implementation of tree node, so that's how I will check. Root dot left is equal to null, and root dot right is equal to null. I should be able to wrap this in parentheses, so it's this entire statement. It gets, yeah, this has to be true. Okay, I'm sure there's a cleaner way to write it, but for now I'm going to focus on implementation. Yeah, at that point we can just return, and then we can just say else, and we'll make tree node temp equal to root dot left. We'll set root dot left equal to root dot right, and then we'll set root dot right equal to temp. Okay, so let me just, I occasionally mix this up. So we're going to take the value that is on the root's left, we're going to store it, and then we're going to take the actual value to the left of the root and assign that to the value to the right of the root. So now the value to the left of the root has the correct value, but the value to the right of the root has its original value. And what we actually want to put there was the original value of the left root, and that is stored up here in our temp variable. So that checks out. And then we just want to recurse, so call this function again, invert tree logic. We're going to want to do that on root.left and invert tree logic on root.right. So let's see. So if I were to just make this if check equal to null, that should still work. It's just that once we get down to a node that looks like this, a leaf node, say this one right here, we would be going through this logic, checking its children and flipping them, and then recursing down to their children. So it would add an extra level to the recursion, which is not really necessary. However, it does make our code a little bit cleaner, although over time the result will be the same. So for the sake of cleaner code, I think I will take this section out. Okay. And to me, that looks correct. Just going to check for any syntactical issues. I see semicolons where they should be. We want to return its root. Let's see, invert tree. Okay, just to run through my, actually, let's check the time. So we have 3 minutes left. I'm going to do a quick run through of my implementation just to check if the logic is airtight. We are given the root of a tree, and we're going to pass it into a function that will invert this tree. And what that essentially means is everything that's on the left side of the root will go onto the right side of the root, and same for every thing below each node. So everything will be flipped. So we have our base case. We have the flipping action, which is one of the first things that you'll learn, at least in Java, or at least for me. And then we're just going to pass it through the function again, going down the left and the right direction. And again, we're not returning anything in this function because all we're doing is modifying the structure of the tree. What we really want to return is up here is the root, which we already have a pointer to, so that should be no problem. And I'm going to run our example really quick. And okay, everything is accepted, so then maybe let's submit. And okay, yep, that seems to be correct. I will stop the problem right here.